Hey guys, hope everybody's doing good. This will be my physical science students' first video like this, so hopefully you guys, this will help you out and you enjoy this. I want to start off by saying that I miss you guys like crazy, and I'm sure that's the feeling's mutual. Better be. But I do miss you guys, and I am thankful that we've got the ability and capacity to continue our classes like this. I know there's a lot of other schools that are much less fortunate than we are, but we do have this ability, so I'm going to use it to its fullest. If you guys have any questions about anything that I mentioned in the video, please email me on Teams or through Teams, message me through Teams, or email me. Just get a hold of me and communicate, please. So I'm going to be stopping and starting the video along the way to bring things up on my screen that you guys will see. So if it seems a little jumpy, that's why. So I'm going to get right in. We're in the middle of this atomic theory stuff, and this is some difficult information to be relaying through this remote learning plan that we've got. Oh, by the way, excuse everything back here. I'm doing my videos down here in the basement in my little workshop. But we're doing this atomic theory stuff, and we're talking about the history of how the atom has been discovered and who discovered what. And I'm not digging in as deep as what I normally would if we were in class, but I'm giving you just the broad strokes, and we're going to be fine with that. So I'm going to be doing some reviewing as we go along today and introducing some new concepts. So at any point, again, if there's something that you don't understand, please make a note of it and reach out and ask me some specific questions, okay? So I'm going to change my screen up and we're going to get into this. All right, you see I've got a periodic table up here, and I'm going to be pulling back to that and referring to that here as we go through. Right off the bat, some of the stuff that you should have come across in your web quest and things related to the periodic table. Our periodic table is arranged by increasing atomic number. So that's number 1, number 2, 3, 4. And it's also set up in a series of groups, which are the vertical columns. Those are our groups. And periods. These are periods running left to right. And here's the way that I always remember that, because I always had a hard time remembering which was which. Think about the way that we read and write. We read and write from left to right. And what do we put at the end of a sentence, or we come across at the end of a sentence if we're reading a period? So periods run left to right, and groups are up and down. Now, you'll see that the periodic table actually has 18 groups. 1, 2, 3, 4, 5, 6, 7, all the way over to 18. Sometimes we discuss those in a different way, and you'll hear me refer to main groups. Main groups. There are actually 8 main groups. So this would be main group 1, main group 2, and then we don't count these transition metals as main groups. So we skip those. And then doing so puts us over here to main group 3, main group 4, 5, 6, 7, and main group 8. So if you hear me talk about main groups, we are referring to those 8 groups that are kind of raised up off of the table, and we're not talking about the transition elements in the main group, okay? But if you hear me say group 14, then, or if I just say group 6 and don't say main group 6, then I'm referring to this group here. This is just group 6 and not main group 6. Main group 6 would be over here, okay? So it's just that little clarification there between main groups and regular groups. All right. So let's get into some info here. Some things that I wanted to make sure that you guys were square on in terms of definitions. So in last week's assignment, we introduced the concept of atomic number. Now, atomic number, when we look at the periodic table, the atomic number are the whole numbers that we see on each of those squares. So hydrogen, there's the atomic number for hydrogen, 1, helium 2, so on and so forth. Okay, so the atomic number is the number of protons in each atom of an element. Remember, all atoms consist of protons, neutrons, and electrons. And the protons are what makes the atom, it gives it its identity. And so the number of protons is called the atomic number. It's the whole number found on the periodic table square. And I want you to think of the atomic number for each element almost like its social security number. Now, every one of you have a different social security number that is distinctly yours and specifically yours. Nobody else has that. And if someone were to find that number, let's say, you were to lose your social security card and they find that and they see that number is tied to you. They can identify you based off of that number. Well, it's the same way with these atomic numbers on the periodic table. If I'm wandering around in nature and I come across an atom and I'm able to pick that up and I'm like, hey, here's an atom there's its nucleus, and I see in that nucleus there's 7 protons. 7 protons in that nucleus. I know without a shadow of a doubt that that is an atom of nitrogen, because no other element has 7 protons in its nucleus. That is very specific to nitrogen. Okay, so we can use these atomic numbers as identifying numbers because they are very specific and individual to each element. Okay, another term, also by the way, right now we want to assume that the number of electrons is also the same as that atomic number, because at this point we're dealing with what we call electrically neutral atoms. We've got the same number of positive protons as we do negative electrons, so that makes it completely neutral. So when we look at that atomic number, we can assume that that also gives us the number of electrons in that atom. Okay. Another term that we're going to talk about, and you should have been introduced to, is mass number. Now, the mass number is essentially the number of particles in the nucleus. And why? Well, because the mass number is the sum of the number of protons and neutrons in an atom. Okay, now that is, I say that it's the number of particles in the nucleus because that's where the protons and the neutrons exist, in the nucleus of an atom. So sometimes we see this equation, if my pen would work. We see mass number equals protons plus neutrons. Okay? So the mass number is the number of protons and neutrons in an atom. And you would have come across that in the practice from last week when, if you had, remember the charts that we were doing, the tables rather, and I had like the number of protons and the number of neutrons and the number of electrons, and then the mass number was over here, and if you were given 10 protons and 12 neutrons, then the mass number should have been 22, because the sum of those equals the mass number. Okay? Now that brings us to another term that you came across, and we're going to talk about it in depth right now. This term isotope. When we start looking at the atoms of an element, we find that some of the atoms differ just slightly in one regard. When we analyze them, they all have the same. Let's say that we're looking at atoms of carbon. Every atom of carbon has 6 protons in there. That's a given. If it didn't, it wouldn't be carbon. Remember, that's the atomic number, and that's the number of protons. So every atom of carbon has 6 protons. But some atoms of carbon will have differing numbers of neutrons in the nucleus. So we define an isotope like this. We say the isotope is just different variations of atoms of an element that only differ in the number of neutrons in the nucleus. So think about them as different varieties of an element. So I always use the analogy of vanilla ice cream. Sometimes you just have plain vanilla. Sometimes you have French vanilla. Sometimes you have vanilla bean. So they're all just different variations of the same flavor. So we're going to look at carbon specifically when we're talking about isotopes. So isotopes of carbon here. Now, I went ahead and drawn a square from the periodic table like we would see for carbon in a typical periodic table. And remember, this 6, this is what we call the atomic number, and that is the number of protons in the atom of that element. Now, also when you look at a square on the periodic table, there's always a second number on there too, typically. And usually that number is a decimal. So if you look at carbon on a standard periodic table, now it doesn't have it over here on this one just because this is kind of simplified. We just have the atomic number. But usually there's a second number on there, and that is a decimal. Now, some people will misname that as the mass number. That is not the mass number. We'll talk about why. This is actually called the atomic mass, and that's different than mass number, and we'll dig into that in a second. All right, so here is what we're looking at with carbon and isotopes of carbon. Okay, just like there are different kinds of vanilla ice cream, but it's all vanilla, there's different forms of carbon atoms. So one such carbon atom, and this makes up the majority of carbon atoms in the universe, is carbon-12. Okay, and you see I've written that carbon-12, and this 12 is the mass number for this particular isotope. So carbon-12 has a mass number of 12. And what does that 12 mean? Well, that 12 being the mass number just means that there are 6 protons and 6 neutrons in the nucleus of a carbon-12 atom. Remember, the mass number is the sum of protons and neutrons. All right, now this number over here that I've got is a percent. What that means is that this is called the percent abundance, and that just tells us that 98% of all carbon in the universe is this flavor of carbon. It's this kind of isotope. It's carbon-12 isotope. All right, so 98% of all carbon is carbon-12. Another form of carbon is carbon-13. Carbon-13, now notice, has a mass number of 13. Now, that 13 indicates the sum of the protons and neutrons is 13, so notice our number of protons did not change because we're still dealing with carbon, and all carbon has 6 protons, or else it wouldn't be carbon. What did change, however, was the number of neutrons. So whereas carbon-12 had 6 protons and 6 neutrons for a sum of 12, carbon-13 has a sum of 6 protons and 7 neutrons for a sum of 13. Now, carbon-13 is the rarest form of carbon, and it only makes up 0.01% of all carbon atoms in the universe. Okay, so that's the second form of carbon. There are actually, There are actually 3 forms of carbon, and change the color back on that. The third form of carbon is called carbon-14. Now, you may have heard of carbon-14 when we talk about carbon dating, where we use radioactive carbon to measure the date of old stuff. Yeah, that's what we're picking up on, is carbon-14. So carbon-14 has a mass number of 14, which means there are 6 protons and 8 neutrons. And it has a percent abundance of 1.8%. All right, so notice the only thing that has changed between those 3 forms of carbon is the number of neutrons. So all 3 of those are different variations of carbon, but they are still carbon. Now, here's how this works. So some people will ask me, well, how do I, if I'm holding a piece of carbon, how do I know if it's carbon-12, carbon-13, or carbon-14? That's not how that works. Okay, so I don't have a chunk of carbon here with me, but let's say that this little wood block represents a big chunk of carbon, and let's say it's just a big piece of charcoal, which is all that carbon is. So it's not that this chunk of carbon is a chunk of carbon 12, carbon 13, or carbon 14. It's all of the isotopes. So if I say that carbon 12 is 98% abundance, that means that 98% of this chunk of carbon here is carbon 12. If carbon 13 has a 0.01% abundance, that means that 0.01% of the atoms in here are carbon 13. And likewise, carbon 14 has a 1.8% abundance. So that means out of all the atoms in this chunk of carbon, 1.8% of those atoms are carbon 14 atoms. Okay, so that begs a question then. When we look at that square on the periodic table and we see that number down there that says 12, and we say that that's an atomic mass, well, which one is it? Is it carbon 12, carbon 13, and carbon 14? Is it carbon 12 because this number is so close to 12, 12.01? Well, that's when we get into a discussion of mass number versus atomic mass. Okay? When we're talking about mass number, notice a mass number is very specific to each individual isotope. So over here, if I'm talking about mass number, I'm referring to a specific isotope. So if I'm talking about carbon 13, I don't say carbon 13 has an atomic mass of 13. I say it has a mass number. But atomic mass is that number, it's that decimal that we see on the periodic table. That's that decimal number. Okay? So what that decimal number actually is, so if we're looking at carbon, get my pen back. When we're looking at carbon on the periodic table and its atomic number is 6, and we see that it has an atomic mass of 12.01, that decimal number is actually a weighted average of the masses of all isotopes of the element. So remember, carbon 13, or carbon has carbon 12, carbon 13, and carbon 14. So when we calculate the mass for carbon, we just can't say, oh, carbon has a mass of 12. Well, that's not true, because there are some carbons that's got a mass of 13 and a mass of 14. So what we have to do is we've got to take into account those three masses of all of the different isotopes. And not only that, notice it's not a straight average. We just don't average 12, 13, and 14 together. If we did, that would be 13 instead of 12.01. It's a weighted average, which means we have to take into account that percent abundance. Now, you may have had teachers that do a weighted grade where tests count for so much percentage of your grade, or homework counts a certain percent. It's the same thing. So when we calculate atomic mass, we have to take into consideration all of the isotopes and their percent abundance. Okay? So make sure that you key in on the different and correct usages of those terms, mass number versus atomic mass. Mass number is talking about individual isotopes. Atomic mass is we're talking about the whole element and all of the isotopes. Okay. All right, so now I'm going to do a little bit of a review, and just I want to make sure that everybody is clear on some things that we should know at this point. First, all atoms are made up of protons, neutrons, and electrons. Those are our three subatomic particles. Protons and neutrons, they're located in the nucleus of an atom, and also protons have a positive charge. Sometimes they're written like that. Neutrons are neutral, they have no charge, and electrons have a negative charge. Electrons are found orbiting around the nucleus in a three-dimensional cloud. Okay, we'll talk about that in a minute. And all three of these items have been part of your work over the past couple weeks with our remote learning plan. So hopefully those ring a bell. If they don't, you need to communicate with me on that. We've talked about the terms mass number, atomic mass, and isotopes. Talked about the periodic table arrangement and periods and groups. And now we're going to focus in a little more on the atomic models. Now, you guys had the activity where you had to illustrate the different atomic models. And what we find, Democritus and John Dalton had a very similar model where they said that an atom was basically this sphere of mass. So it was just basically a circle. Okay. Then we move to J.J. Thomson. And J.J. Thomson had this model called the plum pudding model. Plum pudding. Now, back in the day, plum pudding was a popular dessert, and it was kind of like a fruit cake where you had you had this kind of a cake. It wasn't a pudding, and it was really popular to put raisins in there. And he called it the plum pudding model because J.J. Thomson said, all right, I think that an atom is this big positive sphere of mass. So the whole thing is positive. And then scattered randomly throughout there are these negative electrons. They're just kind of randomly through there. All right, so there's my negative electrons. And he said that he thought that the negative electrons were just kind of randomly scattered in there like raisins would be in plum pudding. Now you can think of it as like a modern day chocolate chip cookie. If you get a chocolate chip cookie, you don't have chocolate chips just located in one spot on that cookie. Hopefully they're scattered throughout the entire cookie. So that was Thomson's model. And then we went to Ernest Rutherford, who stepped it up a little bit, and he said, okay, I now know that all of the positive particles exist in this nucleus here. Okay, so all the positive particles are in this nucleus, and the negative electrons are kind of zooming around out here in this orbit. So that's where my electrons are. And actually, you probably recognize Rutherford's model. Anytime you see an atom somewhere, and it's got that look to it. And it's technically not correct because Rutherford's model has these these electrons in this two-dimensional orbit. They're just going continuously like a solar system. All right. Okay, so that was Rutherford's model. And now that took us up to Bohr's model, Niels Bohr. And the Bohr model looks like this. Bohr said, all right, yeah, all of the positive particles are in the nucleus, so all the protons are in the nucleus. But he said that the electrons are also going around that nucleus, but he said that the electrons are existing in these energy levels. He said that electrons have to go around in these energy levels. So I'm putting some electrons there. So the Bohr model kind of looks like almost like a target, where the bullseye is the nucleus, and then those concentric rings are the energy levels. Okay, and that's what we're going to look a little bit more in detail on now. So Rutherford, Bohr. Now, we also have our current model, the electron cloud model, that is similar to the Bohr model in some respects. So Bohr wasn't far off, but where the Bohr model placed the electrons in two-dimensional orbits, the electron cloud model, our current model, electron cloud model, if this is our positive nucleus, the electron cloud model puts these electrons in this three-dimensional orbital, and it makes it like a sphere. So think about like a hamster ball. You've got the hamster in the middle, that's the nucleus, and then this round sphere outside of it, and that is the electron cloud. Okay, but we're going to focus on the the Bohr model right now, because here's what we need to know in terms of electron placement. For now, the number of electrons will be the same as the atomic number, so electrons the same as protons. Electrons orbit around the nucleus in a very specified way. They're not just randomly out there. Electrons exist in energy levels, and each energy level can hold a certain number of electrons. And while the Bohr model is not the most current model and the most accurate, we still use it quite a bit for teaching and for illustration. Okay, so that's what we're going to use today. And also, here's a big help to you guys when we're learning to place electrons. The periodic table can actually help with electron placement. And how? Well, the period number in which the element resides indicates how many energy levels are going to be needed to hold all the electrons. So for example, if I am looking at an atom of magnesium, I know that I'm going to need 3 energy levels to contain all of the electrons for magnesium, and there's 12 of those. Okay, likewise, if I have an element that's in period 2, all of these, it's going to take 2 energy levels to hold all of those electrons. Okay, and also, the next point, the main group number indicates how many electrons are in the outermost energy level. And those are called valence electrons, and we'll come back to that. All right, so here's how this looks. Here's some examples. And I've got a Bohr model up here, and I told you it looks like a target. That's what it appears to be. So let's, as an example, let's start off and say we're going to draw the Bohr model of, let's go with helium. Now, if we look at the periodic table, we see that helium has an atomic number of 2. So we've got 2 electrons that we've got to place. All right, now, here are some things that we've got to know. This first ring, so that means if we've got helium, that means that there's 2 protons in the nucleus here. Okay, and right now we're just going to look at the protons. There's definitely some neutrons in there also, but we're not focused on the neutrons at this point. Okay, so if I'm helium and I've got 2 electrons, my first electron is going to go in this first ring, which is what we call an energy level. So this is going to be the first energy level here. Okay, so the first electron is going to go there. Now we've got 2, and the second one is also going to go there, and I'm going to place it like this, so they're symmetrical. Okay, and that's it for helium. So the Bohr model for helium is just the nucleus, then you've got 1 ring with 2 electrons. Now let's clear that off, and let's move up and pick one with a little bit more. Let's say we've got carbon. Now let's go on up to oxygen. Okay, oxygen. If I look at the periodic table and I see that oxygen has an atomic number of 8, which means that it's got 8 protons and 8 electrons. Okay, so I've got to place 8 electrons here. Well, I'm going to start off with just like I did for helium and put 8 protons there. My first 2 electrons are going to go in this first energy level here. Okay, now here is a new rule. The first energy level, let me write this a little smaller so I've got room. The first energy level can only hold 2 electrons. So a max of 2. So at this point, that first energy level is full. So I still have 6 more electrons to place. So here's how this works. So there's the first electron, there's the second, Here's the third electron. Now I want to go in a clockwise circle here as I place the others. So I got to place 8. So I placed 1, placed 2, I placed 3, there's 4, there's 5, there's 6, and now I can start to double up. And I want to pair these up. There's 7, and there's 8. Okay, so I've placed all 8 electrons in this Bohr model for oxygen, and that's it. Okay. All right. So another rule. Okay, so I paused the video and I made this some of these bullet points up here to help you out. So the first energy level holds a maximum of 2 electrons. The second energy level is full because it only holds a max of 8 electrons. The third energy level holds a max of 18. And at that point, that's when it starts, there's some higher level chemistry stuff there with the third energy level, so we won't go past that. So I'm going to do another example here, and I'm going to relate it back to the periodic table. So let's look at, we've mentioned magnesium before, so let's look at magnesium. Magnesium, Mg. So if I look back at the periodic table here that I've got at the front of this slideshow, I find magnesium right here. And magnesium has an atomic number of 12. So that tells me that I've got 12 protons and 12 electrons. So I've got to place 12 electrons in the Bohr model. Okay? 12 electrons. I'm going to change my color over here just for some variation. Okay, so 12 electrons. Well, my 12 protons, of course, are going to be there in the nucleus. So now I'm going to start placing my 12 electrons. Now, how many does this first energy level hold? Of course, 2. So there's 1, and there's 2. First energy level holds a maximum of 2. So think about this as like a parking garage. If you go into a parking garage, you know, one of those tiered parking garages like you go to in a bigger city, let's say you pull into the bottom and there's only 2 parking places there at the bottom, and there are cars in both of those. Well, those spots are full, so you're going to have to go up to the next level. So we go up to that next level. Now we've got to place 12 of these. So the first 2 are there. The second level holds a maximum of 8. And remember, we fill that in a clockwise direction. So there's 1, 2, 3, 4, 5. And I'm using the letter E there just to signify electrons. So there's 6, 7, and 8. Okay, so at this point, I've placed 10 electrons. My first energy level is full with 2. My second energy level is full with 8. So the remaining 2 have to go here in that third energy level. Alright, so remember, this is the first energy level. This is the second energy level. And this ring here is the third energy level. Now, remember the point that I made about the periodic table helping you as you're drawing these. Then let's look at magnesium again. And we find magnesium is in the third period. So the number, the period number, tells us how many energy levels it's going to take. And sure enough, it took us 1, 2, 3 energy levels to contain all 12 electrons. Okay, and I said that the main group number that the element's in, let's go back to this point here, the main group number indicates how many electrons are in the outermost energy level, and we call those valence electrons. So if I look at the outermost energy level here, I've got 2 electrons in the outermost energy level, 2. So going back to the periodic table, look at magnesium. What group number is he? Main group number? He is in main group 2. Okay, so if I were to draw the, remember our main groups, 1, 2, main group 3, 4, 5, 6, 7, and 8. So if I were to draw the Bohr diagram for neon really quickly, Neon is element 10. Neon is element 10, so that means 10 protons and 10 electrons. So the first two, 1, 2, the next 8, 3, 4, 5, 6. I've already placed 2, so I got to place 8 more. 1, 2, 3, 4, 5, 6, 7, and 8. So I've placed 10 electrons now. So notice how many electrons are in that outermost energy level here. Now technically that third ring right there would not even be in existence because we don't need it. So that means that we've got 8 electrons in this outermost energy level right there. Well, 8 electrons corresponds to this main group number of 8. And period 2 indicates that we only needed 2 energy levels to hold all of those electrons. Okay. Alright, so that's going to be it for today. Your work for this week's RLP is going to be working with this Bohr model and introducing some of those new terms, and also maybe some possible review on the isotope and the mass number stuff from last week based off of your guys' feedback. So I can't stress enough the importance of you guys letting me know if you've got issues with something or a question. So just keep those rolling in, and above all, please check in with me on Teams to let me know that you're able to view things. And that essentially for me is kind of like taking attendance when you guys let me know that you're able to see everything. Alright, so until next time guys, I hope everybody is well. I hope you're staying safe. I miss you guys, and please let me know if there's anything that you might need from me. Alright, see you guys.